Okay, so let me just check. Okay, yeah. Hello, everyone. Good morning. Welcome to CGO, and welcome to our tutorial on deep learning for compilers. So it'll be hosted by myself. I'm Chris, and then Dibyendu and Sandhya, who are joining from Intel. So we've got a pretty straightforward program. We've got 3 parts of roughly an hour each. So the aim is that we're going to have about a 45-minute talk per person, and then leave time for about 10 minutes of Q&A, and then there'll be a 5-minute break in between each of the talks. This will be recorded. I'll figure out where to put it online, probably on YouTube, and get the URL uploaded after this. The 3 talks are, I'm going to talk about learning over programs and the difficulties or challenges of representing programs for machine learning. Dibyendu is then going to give a talk about the applications of deep learning within compilers. And then finally, Sandhya will give a talk about the challenges and research directions. Now, just a bit of housekeeping, Dibyendu is currently traveling, so he will actually be joining us this session a bit later. So he will give his talk last, and Sandhya will go after me. So with that, I think that's all the housekeeping. I'll just say, in general, if try and keep the questions towards the end, that would be very helpful. There's a chat, so feel free to just type your questions in as soon as they come to you, and we'll take a look at the end. All righty. So we're talking about deep learning for compilers. To begin, let's just set up the motivation of why it is we're interested in this topic. So I'm going to begin with the premise that building optimizing compilers is this like a Sisyphean task. You have compiler engineers forever pushing the boulder of performance up this hill. So why is this so challenging? First off, is that compilers are phenomenally complicated. There are hundreds and thousands of moving parts within them. Tuning every single one, they're typically kind of interdependent, and so if you twiddle one aspect of the compiler and the other aspect needs tuning. Many of the tuning problems inside compilers are NP hard or worse. And what makes this Sisyphean is that you tune your compiler. Some engineer tunes their compiler for a specific workload on a specific version of a compiler for a specific hardware architecture. But then one of those 3 things is bound to change. So the compiler keeps changing because people keep adding new features or updating it. The hardware keeps changing as we move to new and more exotic architectures. And even our workloads keep changing, and different workloads need to be optimized in different manners. So the result is that our optimizing compilers don't give us the performance that we would like. The downsides to this are pretty obvious. One is that bad heuristics means wasted energy, which is not great. And it means that there's this gap between the theoretical performance that our hardware offers and the actual compute performance that our software achieves. And we feel that over time that this performance gap is actually widening. So enter deep learning. What the idea is, we're going to take this, instead of relying on our compiler engineers to, like hand tune our compilers by hand, we will turn it into a data science problem. What we'll do is we'll collect a bunch of examples, where an example is like a program and the way in which we have empirically determined it should be optimized. Collect a bunch of these examples. We're going to learn from those examples a heuristic. So there's 2 advantages to this. The first is that we have taken the human out of the loop. So we're no longer reliant on our compiler engineer to hand tune our compilers. And the second thing is we've turned this into an automatable process. So when our compiler changes, or when our hardware changes, or even when our workloads change, we can repeat this and get a fresh heuristic. So at a very high level, the way it works is we take our program, our thing that we are compiling, and then we need to turn that into a set of features. So let's just think of it for now as a vector of numbers, and I'll be talking about how we'll do that for the duration of this talk. But the idea is, if we can take enough of these feature vectors representing different programs and combine that with the best optimization decision that we can determine empirically by trying lots of different options and measuring performance or measuring whatever it is we want to optimize for, then we can turn this into a supervised machine learning problem. And that will give us a model. So the model learns over our features and the parameters, and then our model becomes the heuristic. We embed that heuristic inside the compiler. And then when we want to compile some new piece of code that we've never seen before, we just map it into that feature space, and then the model will give us a prediction for how we should optimize it. So if we look at like an overview of how this typically looks like in academia and in industry, we kind of have a flow chart that looks kind of like this. We've got on the left side a bunch of training programs. So these are our benchmarks, the things that we're going to learn over. Each of the programs might have their own set of data sets and their own runtime inputs. And we then run these through typically some ad hoc set of scripts, which will compile them with the different optimization options and tell us in order to determine which one gives us the best performance for each of those programs. And then we have some kind of feature extractor, which is a thing that will take that program and turn it into a vector of numbers. And then we combine those best decisions, those feature vectors, that gives us a set of training data from which we can learn our heuristic. So in this first hour, I'm going to be talking about that bit there, which is the feature extraction. And then Dibiendo in the last part of today's tutorial, we'll be talking about the different applications for ML. And Sandhya will be talking about the overall kind of challenges and interesting research problems. Okay, so before we get stuck in, I just thought it'd be interesting to give a kind of very, very reductive, but kind of a very high level history of how we got to where we currently are. So way back when, we have known for a very, very long time that iteratively evaluating different kind of optimization decisions is a good way of finding out what will give us the best performance. This process is typically called auto-tuning. It's the idea of evaluating different candidates empirically in order to determine for a particular workload what optimization decisions you should make. And the idea is pretty straightforward. You just enumerate your space of options, like what are the optimization decisions you need to make. You try all of them, and then you select the one which gave you the best performance. So it works very well in practice. You can date it back to at least the 1970s, probably earlier. The thing is, people didn't bother writing research papers about it because the approach is quite straightforward. But so an interesting thing with this is that one of the kind of downsides is that although empirically we can determine the best configurations through auto-tuning spaces typically are vast, like millions and millions of points, and actually enumerating the entire space would be prohibitively expensive or impossible. So in 1998, some researchers from the University of Edinburgh and elsewhere got together, and they came up with the idea of what if we could use machine learning to try and predict which parts of a very large auto-tuning space we should look at. So rather than just enumerating everything blindly, we'll use this machine learning to guide a search through a space. So that was a very impactful paper, and that effectively launched the combination of machine learning inside compilers. So the next milestone I want to point out is in 2003, a promising master's student called Chris Latner released LVM, which was successful because it modularized compilers, which is fantastic for doing research, especially in the case of like ML compiler research, because it enables you to kind of like isolate the particular point of the compiler that you want to focus on and swap out, and without worrying about the rest. So in 2008, there was a paper called Malpost GCC, which marks the first, I would say one of the most important large, well-funded collaborative efforts to actually shove machine learning inside of a real production compiler, targeting GCC in that case. Now, there's a lot of papers that are missing over this. This is by no means complete, but there is kind of this trickle of papers coming out of academia in which they're taking individual optimization heuristics and replacing them with machine learning models. Now, in 2012, we had the birth of deep learning with AlexNet. And now things start getting a bit cramped on our timeline because in 2015 and 2016, we had TensorFlow and PyTorch released respectively, which kind of really accelerated progress in this field by making it much easier to play around with these new deep learning models. We also start to see a kind of explosion in the different domains in which deep learning was trying to be applied. So we had, like convolutional neural networks and a renaissance in deep language modeling. And then we also had things like the paper I'm pointing out here is the graph neural network, which came out of MSR in 2015. Oh, I should say as well, I forgot to mention this at the start. We will have our slides available as well. So all of these clickable links we will be available afterwards. Now in 2017, so 2 years after the release of TensorFlow, we figured out, hey, it would be good to try and shove this deep learning stuff inside our compiler. So the DeepTune paper was, I think, the first case of that. And then it isn't until we get to quite recently, so 2020, that a very important milestone was reached by MLGo, which was the first actual upstream support in LVM for a machine learned heuristic. So this isn't like Malpost where you're forking a compiler and then retrofitting a bit of machine learning into it. This is native, like first-class support for a machine learning model within a real production compiler, and it was used in production. And then 2020, we also had the release of Compiler Gym, which is a toolkit which aims to make it accelerate progress in this area by taking away a lot of the engineering challenges and just trying to make it as easy as possible for everyone to join in. And now we've got things like the code optimization competition that we're running at ICSA this year. Okay, so that was my whirlwind recap of 50 years worth of progress. And now, so we're now going to begin with my big topic for today, which is learning over programs. So there's 3 approaches to program representation that I'm going to cover: handcrafted features, deep language modeling, and graph reasoning. So I've picked for each of these 3 contrasting areas a single paper to discuss, but there are many that we could have chosen. Okay, and then for each of these 3 papers, I will also be focusing only really on one particular thing for time. Let's start with our discussion of handcrafted features. In the introduction, we had this idea of, okay, we'll take a program and we'll turn it into some numbers. And the numbers are the thing that we're going to learn over. Now, how do we do that? The way that the kind of first approach that people tried, and it's still a very effective approach. So the paper I'm going to be talking about today is by Nadav, and it was from this year on trying to predict profile-guided optimization profiles. The approach is we take the program, and then we'll typically use some kind of IR, like a control flow graph, data flow graph, one of the compiler's internal representations. And then we'll write an analysis that operates over that compiler IR, and it will extract some properties of it. Typically, they might be counting things. So, for example, it could be counting the number of instructions, or capturing the maximum depth of your loop nests, or your density of arithmetic operations, or maybe your loop trip counts if you have those available to you. So this paper that I'm highlighting in this first part is the idea is that we're using machine learning for profile-guided optimization. So profile-guided optimization, the idea is, if you're not familiar, you run you compile your program with some instrumentation, you run it, that gives you a set of profiles, and then you recompile your program, this time with those profiles, and the compiler can take better optimization decisions because it knows more about how your program will actually be executed. Now, the problem with PGO is that it's not straightforward to deploy because it requires multiple steps for your build. It even requires this kind of like iterative process whereby there's a feedback loop between your profiles and your optimizing compiler. So it's not used for everything. So in lieu of actual profiles, LVM has got a set of hard-coded rules which try and predict what the profile would look like for a program without actually having access to it. So, for example, it might try and predict the branch weights coming off of the individual branches. So there's this analysis passed in LVM called branch probability info, which you can all take a look at. It's on GitHub. It's thousands of lines of code that has been developed over a long time by dozens of experts, I think over a decade. And the idea is that I've got a screenshot here of a single heuristic within that giant analysis. And it does things like, it basically tries to make educated guesses for all of the different kind of possibilities for branches over how those branches would behave. And in general, it's pretty good. But it's not as good as actually having the real profiles. So can we instead predict the profiles? So the idea, or Nadav's idea, was, hey, if we take our actual profiles, we've got this perfect case whereby we've got the source code, we've got the actual ground truth labels, which are the real branch weights as measured from profiles. So what if instead of getting thousands of engineer hours worth of effort to develop a heuristic with lots and lots of if-else cases, what if we instead just learnt that if-else kind of nested decision tree, explicitly in this case by using a decision tree. So we'll take a bunch of features, which are the kind of features that the actual heuristic uses when trying to make its guesses, and we'll just shove those inside a CSV file, one row per branch. And then we'll combine that with the labels that we measure through actual profiles, and we'll see if we can learn that correlation between the features and the labels. So the advantages of this handcrafted feature approach is that it's very interpretable. everyone understands what the number of instructions means, or because it's based on these things that the compiler knows, you can understand how the compiler has arrived at those particular feature values. It's also typically very fast to extract. So if we are dealing with information extracted from compiler analyses, it might be that the compiler already has that information available to it, cached, and you're just writing it out to a feature vector. Or even if you have to compute new things, the compiler is typically quick and has these nice data structures which make it very easy to compute new analysis values. The other advantage is, because you're typically only dealing with quite small amounts of data, like say, for example, 50 floating point numbers as your feature vector, that's only 200 bytes worth of information. So it's actually very fast to process as well. So I think what makes this particular paper that I've chosen by Nadav interesting is that it really focuses on the inference side of things, and it has measurements showing that in his case, he can perform over 100,000 inferences per second per compute core, which is a very nice thing if you're considering shoving this inside of your production compiler. Now, the drawbacks. So the problem number one is that it is difficult to get right. There is no golden solution to be able to tell you that the feature vector you have chosen is correct or is as good as it could be. So how do you even know when you're done? Typically, the way it works is that you kind of end up in this iterative process where you've got some like validation set, some training set, and you're kind of iterating on trying different feature combinations. The features and the model are intertwined, so you typically have to it's like a nested loop, searching over features and also searching over models until you find a combination that works well on your validation set, and then you hope that it works well on your test set. So it's a very time-consuming process. Worst of all, though, it is very repetitious. So features that work particularly well for one problem might not necessarily work well for another problem. So every time you want to apply machine learning to a different part of your compiler, and there are lots of different places that you may want to do that, as Divyendo will talk about. Every time you want to do that, you need to start from scratch, building up a new feature set, or restarting this iterative feature design process. So what are the kind of ways in which you could fail? I'll visualize three. Imagine you've got this two-dimensional space that you're trying to learn over. And you might have, let's say, a bunch of triangles, a bunch of circles. And what you want to do is you want to be able to learn to differentiate triangle from circle. So what are the ways in which you can fail? First way in which you can fail is you just pick irrelevant features. So this is actually, in compilers, it's quite easy to do. Imagine it's not obvious what properties of a program actually matter when you're trying to predict how that program behaves. So it's easy to come up with the relevant features, and if you come up with the relevant features, you can see that there's nothing to be learned there, and your model will struggle. Another way in which you could fail is that you could just be missing this like extra feature, this one extra dimension that would tease apart a bunch of programs. So in that case, you could just have an incomplete set of features. Now, a third way in which you could fail is that it could be that your features are perfectly fine. Like on the right there, we could see that you could draw a circle around those triangles. But what if you were dealing with a model which could only do linearly separable features? So it could be that your combination of features and model means that you don't end up learning what you want to. In that case, you have to look into like feature transformations or look at a different model. So those are just kind of three of the challenges that we tried to address when we start thinking about another way, the second way of modeling programs for machine learning. And that is through taking the idea of language modeling. So the paper I'm going to talk about here is one that I wrote in my PhD. And the idea is pretty straightforward. It's rather than thinking of feature design as a compiler challenge, like trying to reason about the program, reason about what the compiler knows about that program, let's instead treat it as a language learning problem. So we already have, in deep learning, we have these tools for feeding through opaquely natural language in order to reason about that language, like text classification. And since programming languages are a language, what if we could repurpose those tools for reasoning about machine code, or rather reasoning about machine languages? So the way it works is we're going to take this high-level approach in which we've got our feature extractor to generate our feature vectors, and we'll just short out that bit of the circuit, and instead we'll just learn directly over the programs and use those as our training data. So the way we're going to do this is we're going to take our program code, as in literally the source code that makes up a program. We're going to feed that into a neural network, we're going to first go through this thing called a normalizer, where a normalizer is a thing that's going to strip out a bunch of stuff that we think is irrelevant, things like comments and like irrelevant bits of the code style. We'll have like enforce a consistent variable naming scheme, that kind of thing. And then we're going to feed that through a tokenizer. A tokenizer is going to chop up our string into a sequence of tokens, which we'll then give into a deep language model. So in this case, we're using an LSTM, which is a long short-term memory network. And what it is, it's a recurrent neural network. So you can feed in a sequence of inputs, and then we take the final state of that network. And that's our kind of summary. That's like our automatically learned features that represent that source code. And then we take that fixed size vector, feed it through a traditional normal deep neural network, and that gives us our output for predicted decision. So the difference is, rather than hand extracting our feature vector instead ourselves, we're instead going to feed a recurrent neural network a sequence of code, and it will do that feature generation for us. So the one aspect I want to talk about in just tiny bit detail is the tokenization, which I think is kind of interesting. So the problem that we're trying to deal with is we want to chop up a string of code at the top there into a sequence of tokens. So we want to balance a few things. One way in which we could do it is we could just chop every single character into its own element of a vocabulary. So for ASCII, that would give us 255 elements in our vocabulary, and then we just feed that through our recurrent neural network. But actually, we know that with programming languages, there's a lot of words that appear very, very frequently. So maybe we could have those be part of our own vocabulary, for example, like the keywords of the language. So the way we did it in this paper is we started off with a candidate vocabulary, which is a set of keywords. And then we scan greedily through our string to try and match the longest keyword. And if we do, that's great. That's our encoded output. And if we miss and there's nothing, then we just fall back to being a character level encoder. So by doing it this way, what we do is we try and balance having a nice low level representation so we can encode everything, with also being able to capture these higher level, like recurrent, very frequently recurring tokens, like, for example, type keywords, or in this case, we're dealing with OpenCL, so like the const qualifier, the kernel qualifier. So this gives us quite a compact vocabulary, which can encode a large set of input programs. I've got the chat window up here. I just saw a question from Aditya, which I'll answer now, since this is the right slide for it. So the question is, what do I mean by normalizing a program? So the normalization is, what we're doing is we're trying to get rid of anything that might vary from one piece of code to another that doesn't actually change the semantics of the code. So I should say this is done at a very simple source level. So in this input example here, for example, it will strip all the comments. And you see how the variables here are named A, B, well, there's only two of them, but the variables have a consistent naming scheme, which starts A, B, C, D, E. That's what we call normalization. So it's basically a Clang AS2 rewriter, and it just does some simple stuff like stripping out bits that we don't think actually matters for a machine learning neural network to understand the code. Okay, so the idea was we're replacing this handcrafted feature approach with a approach which could work for any different type of problem. So we took two different optimization problems. One is heterogeneous device mapping, one is thread coarsening, and so to recap the prior art that we're comparing against. For device mapping, the idea is you've got an OpenCL kernel. You want to know whether or not it will be quicker on the CPU or the GPU. So it's a binary classification problem. For thread coarsening is it's like loop unrolling for GPUs. So you're trying to predict a thread coarsening factor. Now, our prior art for this, because they are quite different problems, it's interesting to see that they came up with very different model architectures and very different feature sets. So the models for the binary classification, they used a decision tree. They used some features which they got from an LVM analysis, and then they kind of combined them and scaled them and normalized them to make their feature vector. For the thread coarsening problem, they came up with this kind of really interesting architecture of cascading neural networks operating over this quite large vector of raw feature values, which they then did PCA over. It's quite an interesting approach. In fact, just the design of their features was the topic of two prior publications. But what we're trying to do is we're trying to avoid doing this feature extraction, and instead use a neural network to do our feature extraction. So for our approach, or the approach which we call deep tune, We're going to use the same architecture of two. So you take your code, you feed it through an LSTM via an embedding, and then you take the final layer of that, or the final output of that LSTM, you feed that through a regular DNN, fully connected DNN, and that will give you your classification output. So the difference between these two, although we're learning different optimization problems, there's only actually 3 lines of code we had to change between our model definitions. So the first line, or the first 2 lines of code, I think, was for heterogeneous mapping. They had some dynamic features, so we concatenated them in. And then finally, you had to change the size of the output layer from 2 nodes to 6 nodes, because the different dimensionalities of the labels. So the nice thing is that we found this works pretty well. It did slightly better than the manually designed feature space, which we thought was very nice, because all we're doing is feeding in the source code. But more importantly, we had this idea that what we're doing is, in both cases, even though we're learning different optimizations, like our end goal is to learn different optimizations, we're doing this, the 2 models still have to do the same thing. They still have to, at first, learn how to kind of reason about, in this case, OpenCL code. So we thought, what if there's the ability to do transfer learning? So the idea with transfer learning is you take a set of, you take the network that you train, the set of weights that you have trained after learning for a particular task, and you use that to initialize the weights for the other task, and then you train as normal. So this is kind of like initialization and then fine tuning for different tasks. What we found when we did that is that we get a further nice performance boost, which was a really nice outcome. So the advantages of this deep language modeling approach is that the first pretty obvious one is that compared to handcrafted features, we don't have to make handcrafted features. So we save time. Our compiler engineers can worry about more important things, which is great. But then it has this other advantage that because we're now using the same model architecture for different problems, it enables us to reuse training or kind of leverage the training that we do between different problems. And I think as Sandhya will talk about in her talk, one of the big challenges with compilers is that our data sets are really tiny. So the ability to do transfer learning can be very beneficial. So it's not perfect there. So the drawbacks. The biggest drawback, I think, is that we've taken something where a compiler engineer could reason about the individual feature values, and we've replaced that with a black box. So an entirely opaque, indecipherable black box. So the problem there is that if your neural network makes a bad decision, it's actually quite hard to figure out, to reason about why it makes that wrong decision. So regressions become harder to fix. There's no clear, there's not a clear action from a failure of the model into like how would we change our representation. Second drawback is that it just doesn't suit all problems. So there are things that feeding machine language through a neural network, or for a recurrent neural network, 1 token at a time, doesn't enable it to do. Like, for example, it's not reading the code backwards. So if reasoning about a piece of code depends on a bit of code that it hasn't yet seen, then it can't do that reasoning. But in summary, it can't handle nonlinear code dependencies, and that's for that reason, we are going to come on to our third and final method for representing programs for machine learning. And that is the idea of representing programs as graphs and then using graph reasoning techniques. So for this, I'll talk about the programmable paper, which is from ICML last year. So the idea is it's pretty straightforward. You've got some code, you've loaded it down to an IR because you're dealing with a compiler. And compilers already have lots of different graph representations that naturally represent the different kinds of properties of programs. Like, for example, you've got control flow graphs, which tell you how the flow of control goes through your program. You've got data flow graphs, which can tell you, which parts of the program depend on which of them. You've got a call graph, which can help you reason about how your different functions interrelate. So what we'll do is we'll take these 3 different graph representations, and then we'll kind of combine them into, like, we'll take the union of them and make a multigraph. And then we can feed that through a gated graph neural network, which is a kind of standard way for reasoning about graphs that was developed by GLE in 2015 in MSR, and has been used very successfully in a number of different domains. But I think it starts off with biochemistry. So in compilers, what we'll do is we'll start off by building our control flow graph. So it is derived from the compiler IR, like I said. For the purpose of this demo, we'll look at LVM IR, but we have an implementation for XLA as well. And so we'll start off with this a full flow graph. So a full flow graph is a control flow graph in which every single basic block or every single instruction has been blown out to be its own node, whereas in a control flow graph, normally it's only one block per node. So we'll take our full flow graph, and then every single node will represent it. It needs a label, like some set of features. And so what we'll do is we'll use the text of the instruction name as the vertex label. So in LVM, I think it's about 63 different instructions. And then we'll insert a bunch of edges in between those instructions that represent the control flow dependencies. So there's one kind of interesting bit here, which is that when you've got a branch, so you've got multiple different outgoing edges from an instruction, ideally you want to be able to differentiate them, like you want to be able to know which one's which. So we use this idea of a position. We add like a feature to our edges, which is a position. So if you've got multiple outgoing edges, it could be position 0, position 1, position 2, and that shows you the first, second, and third outgoing edge from a branch. Okay, so we've got a full flow graph. We'll then add in the data flow relations into that same graph. So we add a bunch of graph nodes. So we'll add a node for every unique constant, and we'll add a node for every unique variable. And then we'll add edges between the variables and the constants and the instructions that use them based on their data flow. So for example, at the top there, we've got this switch. This switch takes 3 operands. It takes a variable and it takes 2 constants. So there will be 2 constant inputs and there'll be a variable input. And then we have the edge feature again, but this time the edge feature shows the order in which the order of different operands. So in the case of that switch where it's got 3 inputs, operand 0 is the I32 variable, and then the 2 constants are 1 and 2. So we have one node for each unique variable and each unique constant. So we can see that which variables are reused by which different instructions, and which instructions generate which variables. Okay, the final third part of our graph representation is we're going to add in the call graph. So for this, we take the entry instruction for every function as the entry point to the function. Did that make sense? I think it did. And then for return edges, back to the call site, we take every terminal instruction within the function and insert return edges. I should have said actually, so this graph that we're building up here on the right, in case you were wondering, is the graph for a very simple recursive Fibonacci implementation. So you've got a switch, which is like n equals 0 or 1 or 2, and you've got the 2 recursive calls that you can see. There's 2 call instructions. So in this case, when you add the call graph in, you see that it calls back into itself, and there's 2 possible exits depending on which of the 2 places it bottoms out. Okay, so you take this graph, which has these different edge types, it has these different node types, and each of the nodes has their own feature, which is the text, and each of the edges has their own feature, which is the position. And now we need some way of learning over it. So the first thing we need to do is we need to featureize those nodes. We need to turn them into numeric values. So what we do is we just build a vocabulary. So every single instruction becomes its own unique element in the vocabulary. Every single data type becomes its own unique element in a vocabulary. The nice thing is, because we've kind of broken up the programs at this quite very granular level where we're only trying to encode individual instructions and not, say, an instruction plus its operands, it means our vocabulary is quite compact. So we had a big set of training programs and we derived the vocabulary, and it was only 2 and a bit thousand different unique elements. So compared to a couple of prior works, one of which was trying to encode everything inside the vocabulary. So for example, add an int 32 and another int 32 would be one thing, versus add an int 32 and an int 60, or add of 2 different typed arguments would be a different element in the vocabulary. So that what you end up with there is this big combinatorial explosion of the number of elements in your vocabulary, which gives you really poor coverage when you've got an unseen program. Or there's another approach, which was just ignoring parts of it. So it was only looking at encoding instructions. So we found this kind of point, which we were trying to find a sweet spot, a balance between the 2. Okay, so we've got a graph. We've got our edges. We've now represented all the nodes as numeric feature vectors. How do we learn over it? Well, we learn over it using a traditional kind of textbook gated graph neural network. So these are the 2. These are 2 equations from the gated graph neural network paper. I'm obviously not going to explain the entire thing, but the idea is it's message passing. You have this iterative process of passing these different node states based on the outgoing edges. We just made a couple of, we basically reused the existing approach, which has been used for other domains, made a couple of small tweaks specifically for compilers. So one is that we wanted to learn different propagation, like different weight matrices for the different types of edges, because we figured that propagating call flow versus data flow versus control flow is different. And then we also throw in this idea of a position gating, which we borrowed from the transformer paper, which enables you to differentiate those different edge positions. So it means that, for example, an instruction with a non-commutative operands can be distinguished. And what you do is you do this iterative message passing process, and then that gives you, you finally do a readout. There's two ways you can read out. You can either sum over the entire graph and get a single feature vector out, or what we were looking at in the paper was we wanted to get a single feature vector for every single, one feature vector for every single node within the graph. The reason we wanted to do this is because we wanted to test what is the kind of limits of like fundamental program reasoning that we can do with this. So we came up with this idea of what if we could learn data flow analysis or compiler analysis. So data flow analysis is, very well studied field. You can find it and you can find it in the Dragon textbook and every compiler textbook. It's a very simple set of equations for iteratively iteratively computing a set of properties about the program. So things like, for example, the reachability of different parts of a program, or which parts of a program dominate which other parts of the program. So all compilers have their very fast, effective implementations and correct implementations of these analyses. But we thought, wouldn't it be interesting if we could turn them into machine learning problems? So the idea being that it's not that we want to replace LLVM's reachability model with a neural network, but rather, if we can show that machine learning is capable of learning these analyses, then it kind of stands to reason that any decision that is built upon these analyses or that requires these analyses, it would be able to do better than a technique that was not able to do those kind of analyses. So the reasoning behind it is like, most optimization decisions require reasoning about data flow. Now, we know that what we did is we took 5 standard data flow analyses: reachability, dominated trees, data dependencies, live out variables, and GCSE, and we took a set of programs like just open source benchmarks. We turned them into kind of like supervised machine learning problems, in which we said, okay, given this point in a program, compute for me all of the reachable points, or given this point in the program, compute for me all of the points of the program that this dominates. So we got a kind of like example in the middle there of like an input graph and an output graph. And then what we found is that when we fed this through an LSTM, so the approach from the previous section, LSTMs really struggle with these kind of analyses, because this is exactly the kind of problem solving that requires like scanning non-linearly through a sequence of code. So when you're feeding your code one token at a time through a recurrent neural network, it really struggles at things like reachability, where it needs to know about bits of the code it might not yet have seen. Or it needs to learn about, from a syntactic point of view, very, very long range dependencies, because functions might be spread out across a file. Whereas when you've got this graph representation, well, these kind of dependencies are very naturally represented. So we were able to, using traditional, like standard gated graph neural networks, able to learn these near perfectly. So the advantages of using a graph to represent a program is that it provides a very powerful representation. Like what we're doing is we're taking these kind of well-established principles for how you reason about code that compilers have been using for decades, and using those as the basis for an input, as input for a machine learning model. The kind of key advantage compared to the prior approach is that it enables us to model these very non-linear and also very long-range dependencies within a piece of code. Like, for example, experiments have shown that like recurrent neural networks or LSTMs can struggle to learn anything that over any signal over about 1,000 tokens. And you can imagine that in a piece of code, it might be many, many thousands of tokens between, like a variable being declared and a variable being used. So the drawbacks of this approach are that compared to extracting a set of handcrafted features through an analysis, or compared to even a recurrent neural network, constructing these graphs is very expensive. So if you imagine you're representing a program in which every single variable and constant and instruction has its own node. So for real programs, you might be talking about hundreds of thousands or millions of nodes. So even just constructing these graphs can be expensive, and then processing these graphs, iteratively feeding them through giant neural networks with huge weight matrices, it requires lots of flops. And then secondly, this is still a lossy featureization of the code. So in the case of this programmable representation, we still don't yet have a solution for how to represent literals. So imagine even something very trivial like x equals 5 print x. We don't encode that 5. We can encode the data type. We can say we've got int x is a literal of type 32-bit integer, but the actual literal value is lost. So what this means is that you can't reverse engineer from a programmable graph. You can't go back to the source code. So this means there will be types of analyses that you're not able to do. And then thirdly is that graph processing, as it stands at the moment, struggles with very large graphs. And we typically have very large graphs. So part of it is just the engineering feat of shoving a very, very large graph inside a GPU. That's not normally so big of a problem. There are ways in which you can decompose the graph or just buy a bigger GPU. But there's also things like the learning struggles, like backpropagation, when you have very, very big graphs and thousands of iteration steps in which you're passing these messages across these big graphs can fall over. So there's some interesting challenges to overcome there. So that wraps up the bits that I was going to talk about in this tutorial. So just conclusions. So the kind of promise of deep learning within compilers is that it will enable us to build better optimization decisions than compiler engineers can do by hand. And more importantly, we can do this automatically. So the three kind of different approaches I've talked about today are, one is that you hand craft a set of features by writing your own compiler analyses or leveraging existing compiler analyses. The second approach is you could borrow the idea of natural language processing and adapt that for programming language reasoning. And the third idea is graph reasoning. Someone just scribbled on the screen. I don't even know you could do that in Zoom. Okay, that scribble's not me, but okay. The third, oh, Dave, it's gone. Thank you, whoever undid that. The third approach is graph reasoning, which is represent programs as a graph using the existing techniques we know for reasoning about programs, and then just embedding that inside a machine learning representation. So the kind of key takeaway I want everyone to take from my talk is that it's not a solved problem. So all three of these papers were within the last 5 years, and there are many, many other papers covering variations, and there's lots of interesting work to be done. And also today, we were only talking about the static representation of programs. There's this whole other area which I haven't even touched on, which is how do you represent programs as they appear in flight? Like how do you represent the profiles? How do you represent the dynamic inputs to a program? So there's lots of interesting work to be done, and hopefully that has piqued your interest. So I will love to take questions for the next about 10 minutes, and then we'll take a 5-minute break. And then I believe Sanya will then give her part of the talk. So thank you very much for your time and for your attention. If you've got a question, please just unmute yourself and shout up. Okay, I think I saw Aditya. Did you put your hand up?
I had a small question. Hi, Chris. So sometimes what happens is, let's say when I am trying to compile my code, I wouldn't want to my compilation time would also depend on the optimizations that is being applied on the fly, right? So if I have a complex model, then the compilation time might also increase in that case. So a programmer wouldn't want to have that, because if I want to have my execution time less, I wouldn't want my code to compile for more time. So are there any works which has been done in this area, keeping in mind that the compilation time doesn't blow up or it is in a minimum, like, so?
Yeah, that's a good question. So if I understand correctly, you're asking, are there any works that look both at optimizing the code through machine learning, while also considering the the actual compilation time as part of that.
Correct.
So I am aware, I think I've definitely read papers in which people have looked at optimization time as one of the, as like a multi-objective optimization problem, trying to balance these two tasks. I think the one that I saw most recently was the guys who did what's it called, Anger Bench, I believe their iterative auto-tuning framework lets you specify combinations of those two objectives. You have to be careful how you design your optimization objective, because if your goal is simply to minimize compilation time, typically the fastest thing to do is just do nothing and not optimize at all. So you'd end up with an optimization pipeline, which is a no-op, which would be very fast, but perhaps not exactly what you're looking for.
Chris, I just wanted to, this is Sandhya here, just wanted to add a bit to what you were saying. So, I mean, that's an interesting question, Aditya. Like, I mean, so as Chris mentioned, some people factor in the compile time as in a multi-objective problem. The other case, like people also trade off like the model complexity versus compile time. Even though you might have a complex model which does a lot better in terms of optimized code, they may not want to go for it and keep a lightweight model so that the compile time is not impacted. In fact, this is a point I would be talking about like in my side of the talk. When we talk about what are the trade-offs that happen like when you're going for a machine learning model. In some ways, this is a general problem in compilation also, right? I mean, for instance, like you could get a optimization heuristic which takes a long time to compute and gives you a better decision, but you might trade it off, right? So a similar problem exists in ML, and I probably would be talking about this in the subsequent section. And again, the question also depends on the setting. If you're doing a dynamic compilation like a jitting kind of thing instead of ahead of time compilation, these decisions would also change, right? Interesting question.
Mm-hmm. Yeah, I think that there's some interesting work to be done there. I think off the top of my head, the kind of two papers that I think actually address the problem head on of inference time, which is what you're talking about, like deployment inference time, are the two most recent papers that came out of industry. So the Google's MLGo paper, in which they included measurements of inference time, and they discussed the increased memory footprint of their ML pass. And then the other one was Nadav's paper, which I talked about today, in which there is no dynamic memory allocation, and he benchmarked the single thread throughput. But these are kind of like examples of cases where people have been conscious of performance and so have designed their model to try and minimize the performance impact. I've not seen people try and use that as part of like the objective, like while also trying to minimize prediction error. So I think there would be an interesting piece of work to be done there. Okay, so thank you for the question. Would anyone else like to ask anything? I should say I can't, I can only see like a few names on my screen at a time, so don't use the hands up feature. Just unmute yourself and speak up, please.
Chris, thanks for the talk. What was the reason you left out the literals in the ProGramML representation?
Yes, that's a good question. Sorry, I can't see who asked that. So the reason we left out literals is that we don't know how to reason about them. So that typically, or the way in which we were representing our vocabulary is a one hot vector of, let's say you've got a vocabulary of 100 things, and they might be 100 different keywords. So when you've got a program and you want to map it into that vocabulary, you just take whatever you split it up into those into the lookup table of those 1 in 100 elements in the vocabulary. If you have something that isn't in that vocabulary that you need to encode, there actually isn't. You don't know what to do with it. Normally, you reserve one element in the vocabulary for being the special, like unknown token. So the reason we don't encode literals is that there are an infinite number of them, and we want a vocabulary that is quite. We want to bound the size of our vocabulary. Did that make sense?
Yes, that makes sense. Thanks. This is Brian Chen, by the way.
Hi, Brian. Yeah, I should say there has been work there was a paper maybe a couple of years ago, which was trying to learn over infinite sized vocabularies, I think using like a recursive tree size. I'm not entirely sure actually, but that's one of the interesting unsolved problems, I think.
Thank you.
Thanks for the question. Okay, if no one has got any more questions, then we can end a couple minutes early, which is good. I think everyone appreciates a longer break, right? So we'll pick this up on the hour in 8 minutes, in whatever time that is for your local time zone, where Sandhya will give her talk.
Actually, I do have one more question, if I may.
Yeah, please, by all means.
So let's say I have a compiler with multiple passes that use ProgramML, and I take one IR and convert it into ProgramML graph. Is there a way for me to like incrementally transform the graphs to so that after a certain optimization on the IR, I don't need to reconvert?
That's a good question. No is the short. Unfortunately, the short answer. In the current implementation, that isn't possible, but that's only like an implementation detail. So the way in which we construct the programmable graphs is it's just a visitor pass. So like we take the LVM module, we iterate over all the blocks and then emit our nodes and emit our edges. What we could do perhaps is maintain like a mapping from the LVM instruction objects to the nodes in the graph that we generate. Maybe that would be possible for speeding up the iterative graph diffing. But I'm not actually, that's a good question. To be honest, it might be harder than I think, because with the current API, right, an optimization can only tell you that it modified the program. It won't tell you what modifications it made. So actually figuring out which bits of the graph need updating might not be straightforward, at least for LVM.
Yeah, understand. It's an interesting question to think about. Thanks.
Yeah. Okay, Sandhya, if I stop my screen share, do you want to take over?
Yeah, sure. I'll do that. Thanks, Chris.
Okie dokie. Let me figure out how to do that.
Let me try sharing mine. Chris, can you see my screen?
I can see your slides. Yep, you're upside down.
That's what I was wondering. I mean, I wasn't sure. Like I did. Let me stop the video and restart. I don't know what happened.
I thought maybe you were just in the southern hemisphere or something.
I know. Just a second. Let me unshare and come back. I mean, just give me a second.
Mm-hmm.
Interesting. Whenever I start my video again, like it's showing upside.
So the second speaker today is Spider-Man. I suppose. And so your slides were the right way up, and I suppose that is if we can't fix the
that's a blessing, I think. Just a second, let me see. I have not applied anything. And this is weird. Okay. Oh, rotate. Okay. Now I should be on the right part. Is that right?
I can't see you or your slides at the moment.
Oh, okay. Give me a second. Yeah. Chris, you can see my video, right? Yeah. Hi. Thank you. Now I'll do the share again. Okay. Chris, you can see my screen?
Yep, this all looks good to me. So the recording is still going. We can give it 2 minutes and then we'll be starting on the hour. Because people might have gone for a break. I'm actually just going to go make myself another cup of tea. So okay. Sandhya, if you're ready to go, I think this is a good time.
Sure. Yeah, sure. Thanks, Chris. Chris, am I audible?
I can hear you. Yep.
Okay, great. Thanks. So folks, here is the second, in fact, the third session of the talk, which is about challenges and research directions in applying deep learning and machine learning to compilers. We are sort of switching the session, I would be covering the challenges and research directions now, and then Dibyendu will talk about the applications of deep learning in various compiler optimization. So good morning, good afternoon, and good evening, whichever time zone you are in. So in this talk, actually, first let me introduce myself. I'm Sandhya. I work as a principal engineer in Intel, and my background is that, I work in compiler optimization. In fact, I worked in HP Hewlett Packard as a compiler engineer, writing high-level optimizer code. And then I moved into machine learning and natural language processing for a few years and worked on natural language processing, and then came back into compiler. So I'm sort of right now focusing on applying deep learning, natural language processing techniques into compiler and seeing like, I mean, how we can use these compilers in production compilers at Intel. Given that, like, I mean, the focus of my talk today would be, there's been a lot of work, as Chris pointed out, like, I mean, in his whirlwind tour of like machine learning in compilers, there's been a lot of work in applying machine learning and deep learning techniques into compilers. But when you think about it, like when you look back, like at the graph that Chris was showing, remember, there was this milepost GCC, which he mentioned came out in 2018. And then, like, I mean, the next paper, if you sort of think about, which is sort of in production compiler, is MLGO, which came last year, right? I mean, to 2020, 2021. We have this vast amount of research in compilers where machine learning techniques have been applied for, I mean, like perhaps like 2 decades of research. But you can sort of count on your fingers, like, I mean, how many of them have made it into production compilers, right? I mean, these are all very important, significant, and impactful work, but there has been challenges in getting them into production compilers. So if want to take these research work into production compilers and even address like what are the challenges like in making ML and DL a regular feature in our production compilers. And that's what I wanted, I mean, my talk would be covering today. Like, I mean, I want to focus on the challenges. And of course, when there are challenges, of course, they are like fertile ground for research opportunities. So that would be the focus of my talk. So as I said, like, I mean, the next part of our tutorial would be about Dibyendu talking about where can we apply machine learning and deep learning in compiler optimization, right? So I just want to set the context here, because when we talk about like the challenges, where do you think like we can apply machine learning and deep learning in compiler? Typically, like any machine learning problem has some very preferable characteristics. You want to typically have a large search space which you want to approximate or direct using machine learning. You don't mind having approximate solutions, and you need, I mean, typically if you have a large data set, in our case there would be a large code base or samples which we can use for learning the model. And we have to ensure that the probabilistic nature which is inherent to machine learning and deep learning does not impact like the correctness of whatever we are proposing, right? In compilers, of course, there are like plenty of candidates. We can talk about optimization heuristics. We can talk about phase ordering. For instance, in register allocation or inlining or scheduling or loop unrolling and so on, right? So when we think about this, like, as I said, ML and DL in compiler optimization is not really new. For last 2 decades, there's been a lot of work. As I said, I'm just picking and choosing here. 2008, they had 2009, there was this paper about like unrolled factor learning. And in 2013, there was this paper about inlining heuristics, right? So what are the challenges? As Chris Ladner said once, like none of our current compilers were designed for machine learning integration. So there's a lot of work that can be done to integrate machine learning techniques into our compilers. But because the compilers were not designed from ground up for machine learning, it's really hard to do this outside of a research paper, right? As I said before, when there are great challenges, there are good opportunities for research as well, right? So first, let's look at one problem space. How do we learn compiler heuristics, right? If you think about every optimization, we can model it in 2 phases, right? We have this analysis part and we have the optimization or the transformation, the implementation part, right? The analysis part is typically heuristics. There's no code change, right? Even if you make a slightly non-optimal decision, it does not impact the correctness. It can only impact performance, right? Whereas if you think about the transformation part, you actually implement the optimization, right? You actually go and change the code in that case, it will impact correctness, right? So when you think about compiler heuristics, ideal for machine learning because we want to separate correctness from policy or model. Given the probabilistic nature of machine learning and deep learning, we don't want to have cases where correctness could be impacted, right? So compiler heuristics seems like a good area for this. So if that is the case, what are really the challenges, right? I'm sorry. Just give me a second. Right. So let's first look at how the heuristics, manually written heuristics, are going to be different compared to a model that can be learned using machine learning or deep learning, right? Heuristics are hand coded, right? They are human written code which needs maintenance. Therefore, it has scalability issues as well, right? Whereas machine learned model can, deep learning models can actually automatically extract features, right? But the issue, as Chris also pointed out earlier, is that human heuristics are comprehensible. We can easily maintain them, we can improve them. Whereas when you're thinking about DL models, they're often not interpretable, nor are they explainable, right? But if you have large amount of training examples, the DL models or DL policies, right, they scale much better because they can generalize across data sets. Whereas when humans are trying to code these heuristics, as you all know, you can only factor in a few of them or a few combinations of them, and they may not generalize very well across code bases, right? So that is an issue. So if we are trying to learn deep learning driven compiler policies or heuristics, right? So basically, let me stop here and say we will interchangeably use the word policy or model. And whenever I talk about ML or DL, you can it's encompasses deep learning, reinforcement learning, and machine learning techniques. So I'm using those two things interchangeably. Right. So the first thing is that the day-to-day production use, and this was a question I think Aditya brought up as well, right, during the earlier session. We don't really want the compiler, the user of the compiler to feel that his compile time has increased or something has changed for him just because we are using machine learning or deep learning in the compiler, right? So we want to make sure the production use of the compiler is separate from training of the ML models or policies. So that the user who is trying to use the compiler to compile his code does not really see any impact. See, what he wants is better optimizations and so on, but he doesn't really want to get into whether it comes from an ML or it comes from a manual heuristics, right? I want to make sure my car goes faster, but I don't really want to know what is inside the engine. So we want to make sure we separate the training of the ML models and policies, and they are not impacting an end user who wants to compile programs using the compiler. And we want to make sure there are no impacts on the compile time as well. So when you think about it, this requires that there are two kinds of people who end up interacting in this ecosystem, right? This is normal user or an application developer who uses compiler to compile his application. And then there is this compiler engineer who is actually creating the model, who is actually maintaining the model, performing the bug fixes, and improving the model. And these are two people with highly different characteristics, right? Some of us who are here could be writing compilers, and most of us are, but we also have the other avatar or other behavior where we just use the compiler to compile code, right? So there are these two personas that we need to cater to when we bring in ML or DL inside the compiler, right? So as I said, compiler heuristics are amenable to replacement by machine learned models. So instead of talking about in abstract these challenges, I just want to talk about them in the context of a paper And as we know that there are only a couple of papers which have used machine learning in production compilers, I want to focus on a recent paper, which is MLGO, which came out from Google compiler team sometime, I think, like in late 2020. This is called Machine Learning Guided Compiler Optimization Framework, and it's a very interesting piece of work. I mean, first of all, because like this is being done in a production LLVM deployment. And second thing is they're sort of chartering, I mean, like they're sort of like exploring uncharted territory, right? I mean, they're trying to bring a deep learning model inside a compiler, production compiler, which should scale well, and we should cater to the two kinds of users we were talking about. One is a normal compiler user or an application developer, and other is a compiler engineer, right? So we will wear both these hats and think about what would be the requirements for each of them and how like they address these requirements in MLGO, right? So this is going to be more of a case study. And I mean, the idea is that we are not really looking at, I mean, what were their performance numbers? Did they do better than other state of the art model? That's not our focus here. Our focus here is like, I mean, what were the challenges they experienced while bringing in machine learning and deep learning techniques into the compiler? What were the trade-offs that we made? And how some of these decisions would be generalizable for other compiler optimizations, and what research opportunities this opens up, right? So just to give you the overview of MLGO, the problem that they choose was inlining, right? I mean, there are a lot of heuristics associated with inlining, and they decided to use an machine learning driven policy for replacing inlining heuristics. And when you think about inlining, like you can do inlining for two things, right? You can do inlining to reduce the code size, or you can do inlining to improve performance. They actually opted like to look at inlining for code size reduction, right? And the reason I will talk about it a bit later. One thing is that when you're trying to do inlining for code size, like the reward, or like, I mean, the target you are trying to do is easily measurable. It's a native code size with or without the specific set of inlining decisions, right? So you know, like, I mean, my code size has reduced, so you have a good reward which can guide your policy. As we know, inlining heuristics are complex. And when you think about it, like whenever you're trying to choose an ML or deep learning model, you have a plenty of like different learning paradigms to experiment with, right? You could do supervised learning, you can do unsupervised learning, you can do reinforcement learning. Supervised learning is not viable in this case because supervised learning typically require that the data set should have clear ground truth labels. For inlining, we cannot always say like, I mean, this particular inlining decision is very good or very bad in standalone format, right? So there are no labels, so supervised learning was not viable. So they decided to use reinforcement learning. Basically, the idea is to explore like different strategies and like learn from what they have explored. So RL is the choice they made, and this could be different for different optimization problem, right? I mean, there might be cases where, I mean, as Chris was talking about in his case for profile, for obtaining machine learning guided profile estimation, supervised learning is possible to apply. And there could be other cases as well where supervised learning makes sense. In this case, like, I mean, there are no optimal labels for this task, whether this is the right decision or not. So given that, like, they model this as an RL problem. So this is another factor you might have to consider when you decide to apply deep learning technique in your optimization, right? I mean, what is the type of learning paradigm that I would choose? It would depend on your data set availability, and it would also depend on the overheads associated with it, right? I mean, some of the models might be like learning paradigms might be costly to train a model and even to deploy it in inference. So that's a trade-off that we will have to talk about later, right? So to go back to our older, I mean, like what we talked a bit earlier, you have these two users, normal user and the compiler developer. So what would be the characteristics like, I mean, we would associate with each of them, right? What would a normal user needs? The normal user, I mean, this is very, all of us know this. He is very concerned that the correctness should not be impacted. He is very concerned that, like, I mean, determinism of the compilation should not change. I mean, for instance, if your input source code has not changed, there should not be change in my dot object file generated, because it would allow me like to use the incremental build support. I want to make sure my compile time is not impacted. I also don't want to see added complexity in my pipeline, right? Basically, my build and infrastructure pipeline should not change or should not need new libraries or software packages because I'm using deep learning or ML in the compiler, right? Whereas like these requirements may not exist for a compiler engineer. So what did the MLGo folks do? They made certain design choices to satisfy this user, right? So basically they separated out correctness and policy. We talked about this some time back. In the sense that we are only looking at inlining heuristics. So the implementation or the actual way inlining is done in terms of like making the code change itself is not controlled by this thing. Therefore, like correctness is not an issue. It would only be impacting whether you are able to reduce the size or not, right? And they don't want to have an impact on the compile time. The third important choice they made was they decided that we will not train the model online, which means like the compiler user will never be part of the training loop. It will be an offline training. And we don't want to frequently retrain the model because that would need updates to the compiler. And it should generalize across code bases, right? Okay. Sorry. Just give me a second. Right. Okay. So when we talk about, just one second, there's some problem with my. Okay, right. So now let's talk about the compiler engineer persona. He is somebody who wants to use ML inside the compiler. He is going to do maintenance of the compiler. And he is willing to spend time and effort like to get these compiler optimization passes implemented, models trained, and so on. So he is okay with having an impact on the compile time. He doesn't worry about having his build or release pipelines changed. But he also like wants to make sure that he can efficiently debug and maintain the code, right? I mean, just because we introduce ML, what if it becomes very difficult to debug a regression or a build blocker? He also is okay with experimenting with different training paradigms. So these are two different people. So any ML driven or DL driven compiler optimization that you design, you need to think about the needs of these two personas, and there could be other personas as well. For instance, there could be a build engineer. So when you think about your production pipeline in your compiler, you need to think through who are the stakeholders and how the new optimization that you're designing with ML would impact each of them. But this is the general user, right? I mean, one is a user and another is a compiler developer, right? Sorry, just give me a second. My apologies, like my Zoom screen got some problem. Okay, right. Okay, so I'm hoping that my screen is visible to everybody now. So when we talk about these different personas, they all have different tasks, right? For instance, like once I have a model and the model has been trained and it has been deployed, then the user who is going to use this is application developer or the normal user. And we call this as the release mode or production mode. Then there are other cases where somebody is training a model, improving a model, or maintaining a model. That would be a development mode. So there are these two distinct modes when you are deploying an ML-driven compiler optimization. One is the production mode or release mode. The other one would be the development mode. So you need to make sure any, design choices that you need to think through what would be the implications for each of these two modes, right? Okay. And let's go back. Think about what was the task that MLGO paper attacked, and that is about inlining heuristics for reducing the size, right? If you think about the current LLVM compiler, inlining is a very complex problem, and we have a bunch of heuristics associated with that. For instance, we look at a number of things we compute the static cost for the callee as if it has been inline. And then we compare it with the threshold, and the threshold itself would be dependent on a number of things, whether the call site is hot, whether there is an inline keyword. And we also add bonuses such as based on the callee characteristics, right? Whether it's a single basic block, number of vector instructions, and so on, right? So you have some local characteristics to the call site. There are global characteristics such as the hotness, which is part of the whole call graph. And there could also be various optimization directives or inline keywords, right? So these heuristics are very complex, and that's probably the reason why using deep learning or ML to replace these heuristics makes a lot of sense, right? So MLGO paper tries, I'm not going to get into the details of the algorithms themselves, but at a high level, when you think about it, because there are no good optimal data set or ground truth labels, they use reinforcement learning and evolution strategies for this problem. And one of the ways when you start with initializing the parameters for your deep learning model, you don't want to start off with a random initialization. So they actually use what is called as behavioral cloning. Behavioral cloning is sort of you think about it this way, right? If I think that my standard LLVM inliner is the optimal decision maker, I will use the output from the LLVM inliner as my ground truth label, right? That would be my gold standard. So your behavioral cloning would mimic the standard LLVM inliner, and we learn a model for that. We learn the weights for that, and that is what we would initialize our neural network with. So it's basically starting off, instead of starting with a random initialization, we start off with a weight initialization, which is obtained from behavioral cloning. Okay. And as I said, they decided to use a reinforcement learning kind of approach. And reinforcement learning is pretty popular, for many of these optimization problem where you have a large search space and you don't have a well-defined ground truth labels, right? So the idea is that it's sort of like playing a game. The agent interacts with the environment based on your current state, and he will do some action. It's like taking a step forward or backward, right? In this case, every action will have a reward associated with that, and the action also changes the environment. So based on the reward, we actually tune the policy or the model. So the idea is that I want to change my model or policy to maximize my reward. So in our case, when we think about it, the compiler is the agent. The policy would be the replacement model for the heuristics. And what is our action? Our action is whether I should inline or not inline. And what would be my state? My state is the current state of my call graph. So we'll talk about how we define reward a bit later. But you just keep this perspective in your mind that compiler is the agent who is making an action. The action is to inline or not to inline. And I'm trying to learn the best policy for making this decision. And the state I would have would be my current call graph state, because the problem I'm dealing with is inlining, right? When we think about it, inlining is when you inline a call site, it is not an independent decision in a way, right? We are making a sequence of decision. My earlier decisions, of course, changes the state. So this is a sequential decision-making problem. And so we formulate it as a Markov decision process. And as I said, it's represented by this four tuple, the state, the action, how do you transition from one state to another, and a reward function, right? And we will talk, basically we want to find a policy which will maximize our total reward, right? So in our case, the state space would be the current call graph state and what is the particular call site that is being visited. If you think about it, like at every point, I need to know which state I'm in. And based on my action, I'm going to change my state, right? But call graphs can be quite huge. So it's not very practical, like, I mean, to represent my current state using a call graph. So what MLGO decides to do, they decide to fall back like to using a set of, set of handcrafted features instead of the whole call graph. And we would see how this decision actually impacts like the model that they learned later. Then we sort of like postponed how do we define reward, right? Since we are doing inlining for size, a natural way of defining the reward is how do we see the reduction in size after deciding to inline or not, right? So if I decide to inline, my reward would be the reduction in size because of the inlining. If I was able to delete the callee from the final module, or there is no change because if the callee is not deleted. And of course, if I decide not to inline, there is no reward because like, I mean, my size has not changed. And this is pretty easy to compute for me, right? The interesting thing is, like, as I said, they decided like to represent the state space, because the state space, if you use the entire call graph, is huge. They decided to do this trade-off by representing it using a set of features. And as you can see in the table, like these features are pretty much coarse grained, right? I mean, they have a set of features associated with the caller in terms of what is the basic block count, how many users the caller had. Similarly, callee features, what is the callee, I mean, the number of basic blocks in the callee, how many were conditionally executed, and so on. Many of these are like local features. They are associated with the call site. And they also have certain, I mean, a couple of global features. One is the edge count and the node count. So the point, the key takeaway is that because it's difficult to represent the complete call graph, because of its impact, like in terms of the compile time and so on, they decided to make this trade-off where they represented by a set of these features, and this can impact the quality of the model that they are building, right? So that is a challenge. So when we are using deep learning or machine learning, and we are trying to represent, in this case, they use the reinforcement learning, right? The state space is computationally difficult to represent, right? Because we are trying to represent the entire call graph at each point after when we make a decision to inline or not. And if you decide to use the whole call graph, it can have impact on your compute cost, memory cost. It can impact the compile time. Because of this, they make this trade-off to use a set of features. So this is a challenge. So how do we develop computationally viable state space representation, right? Because this directly impacts the information that's available to the model. We decided to do a handful of features. We don't have the entire picture of the call graph. So how do we deal with this? And second thing, when you think about it, these are only numeric features. So they do not do any kind of like embedding representation of the callee, either in terms of the IR code or source code, right? Again, this is a decision that was made to reduce the memory and the compute cost. And again, this can have an impact on the model quality that you build. So these are a couple of challenges, which brings up the opportunities for research to think about how do we build computationally efficient state space, and how do we do these embedding representation for this task. Either we can build them task specific, for instance, for inlining for size, or they can be like which are task agnostic, right? just as we have these embedding for word to vec or paragraph to vec or contextual vector embeddings for human languages, right? I mean, we need to have very well trained IR embedding representation, which we currently don't have in our compilers, right? The other thing we talk about is like, because it's a reinforcement learning problem, there's a reward. You need to have a measurement for the reward. In our case, the reward is like actually what is the reduction in size because you decided to inline a particular call site, right? If you, basically the way MLGO chooses to go forward, instead of computing the reward at every point, they make an approximation to use a total reward. Okay, so you basically have a trajectory of inlining decisions, and then you compute the native size leg based on that inlining decision, and you use that as your total reward. Preferably, like if you have partial reward, it would again require more compute, and that is why this trade-off gets made. And the idea is like we need to figure out ways how we can come up with reward formulations which are scalable and compute efficient without impacting model quality. See, we are dealing with actually a simpler problem in MLGO, right? I mean, we are only looking at inlining for size. The moment we think of inlining for performance or speed, we need to have actual benchmark runs, which are again going to be computationally intensive, and they can be noisy as well. So, there's a lot of work left in coming up, like for different optimizations, can we come up with task specific rewards? So this is again an open problem which we need to solve, right? And of course, as Chris pointed out earlier as well, you need good data sets if you're like trying to learn if you're trying to use ML or DL model. And for instance, for this specific problem, inlining for size, there are no standard or ready-made data sets. So basically, like, they actually use a corpus and they try to create their own data set. The question is like, the model quality would depend on how big your training corpus is and how general or how representative it is, right? And you want to make sure that you can collect your data. In this case, what do we need? We need to have a set of IR files, and we want to figure out like what is the inline decision given a policy. So you need to make sure you can do this data collection without too much overhead. So that is again something like, we need to factor in when we are bringing in ML or DL into the compiler pipeline, right? So far we talked about how do we train a model. Of course, once you have a model, like, there would be need to improve the model. And this is very much similar to what we have with manual heuristics, right? Basically, like in case of manual heuristics, if there is a regression, we try to performance regression, or we figure out, is there a heuristic that I need to change? Is there a threshold that I need to change? Similarly, in case of when you're using an ML model, you want to identify what would be a good feature to add, right? If you're using handcrafted features, probably like, yes, you can experiment with different features. But when you're using a deep learning model, as Chris also pointed out, the black box nature makes you difficult. The very thing which gives deep learning its power, right? You don't have to hand specify a feature, also becomes the main bottleneck, because now you don't know, like, what is a missing feature, right? So you need to figure out, like, looking at actual regression, maybe like this is what the model is not learning. Should I add it as an auxiliary feature, and so on, right? So model improvement also becomes a challenge to some extent. Then, of course, like, a similar problem exists with debug and fixing as well. First thing is, of course, debugging becomes a problem because of the black box nature. We have talked about that. But what happens, like, if I have, like, there is a case which is failing with the deep learning model, but I don't have time, like, to debug it. I need to give a workaround, right? So when you have manual heuristics, we can drop the optimization, we can give a flag and so on, or change the heuristic. In this case, we would need model training, right? Or we need to fall back to manual heuristics. So what are our key takeaways from MLGO case study that we talked so far? The main thing is that there would be design choices that are getting made because of the impact on the compile time or compute or memory, but this can impact the model quality adversely, right? And we want to make sure compile time does not get impacted. Again, this could mean that you end up training a model offline, or if you want to train a model online, you want to make sure that the compile time is not impacted, which means that the model quality may not be great. And of course, the inherent nature of DL makes it difficult to have explainability for why the model is making the decision that it makes, right? I mean, so far what we discussed was what are the design choices and what are the problems like that MLGO paper talks about, and how did they deal with it, right? So what are our research opportunities per se, like when we think about it? First of all, MLGO made this decision to do inlining for size because it's in some ways it's a simpler problem. It's I mean the rewards are easy to compute. Whereas like if you're trying to do for general optimization problem where speed up or performance is your main criteria, how do we handle this? Because you don't really want to do so many benchmarks runs because that's going to add up to your compute time overhead and so on. So can we figure out like reward computations which are task specific, right? So even when you think about inlining for size, the MLGO paper proposes an alternative reward formulation where they think of like, I mean, reducing the instruction cache lines, I mean, the working set size itself. And that can be a proxy reward instead of computing what is the actual reduction in size by completely compiling the module. So basically, one thing we need to think about when we use reinforcement learning is how do I come up with a tractable reward formulation, right? And the second problem we already discussed, which is about like, how do I have an efficient state representation? Remember, MLGO people decided to make this trade-off because it becomes computationally inefficient to represent the entire call graph. They decided to go for a handful of features, and that reduces the information available to the model. So we need to come up, one way is to think about like how do we build compact representations. The other way to think about it is, can we have pre-trained models, right? I mean, Chris talked about transfer learning approaches, right? And a lot of work in deep learning, for instance, like when we talk about today, natural language processing, like, I mean, transfer learning or foundational models, right? Where you have large language models that have been trained and they can be fine-tuned for specific tasks, right? I mean, GPT-3 or BERT and so on. So can we come up with pre-trained models on compiler IR or optimized IR that can be used to learn these representation? And other thing is like, I mean, you don't want to have just numeric features because compiler has a lot of information and analysis that are graphical in nature, right? Graph representation, control flow, data flow, and so on. So even in this case, the call graph can be represented using a graph neural network. So the basically like the deep learning model that you would use would depend on what task and what is the representation that would be optimal for that task, right? So to conclude, like, I mean, I just want to give a very quick summary of the challenges. We don't have standardized, I mean, see, how did deep learning really catch up? I mean, there's like plenty of data sets today, like, which are standardized. So if you want to learn a specific problem, like, I mean, image recognition or sentiment analysis using a deep learning model, you have like standardized data sets. Whereas like when you think about applying like deep learning to compilers, we don't have standardized data sets. We don't have a very well established experimental platforms, right? And even like some of the data sets that are available are typically available at source code level. They're not available at compiler IR level or I mean code level, right? Intermediate code level. So that's a challenge. So if you want to address this challenge, a couple of ways to think about, can we like synthesize data sets? I mean, can we build new data sets which can be automatically done without having too much of manual effort for different compilation or optimization tasks? And we also need like quick way of doing these experimentation with DL models. And of course, like, I mean, environments like compiler gym, which has come up like recently, like make this process smooth. But there's like a lot of work involved in getting like more environments like compiler gym, which would make like experimenting with deep learning models much easier for compiler developers, right? And the other thing I already talked about, we don't have good pre-trained IR models. So if you want to apply transfer learning out of the box to compiler optimization, it's not going to be easy. We don't have, again, like general purpose IR embedding, though there is IR2Vec paper. I mean, they did release like, I mean, LLVM IR representation, but IR itself changes as you passes through the optimizer pipeline, right? I mean, for instance, like if you look at the IR, like pre-inlining and post-inlining, the context changes a lot. So if you want to get contextual IR embedding, you really want to get IR embedding at different parts in your pipeline, right? So we want to have techniques which can do IR embedding generation across code bases and which are agnostics to different compiler tasks. And of course, the bigger challenge when we build a DL or ML model into a production compiler is that if the model doesn't work well, or you want to improve the model, or if there is a bug fix, you don't really know what is wrong with the model because the DL is a black box. So as you know, this problem is very common. I mean, it's not just for compilers. I mean, when you apply deep learning to mission critical or life impactful decision, explainability become key. And there's like a lot of work in generating rationals or, I mean, explainable supportive statements for any decision that deep learning model takes. And these rationals would be quite different in the context of compiler, right? Basically, we are trying to come up like why a deep learning model made the decision to inline. So we need to come up with techniques that can generate rationals for DL-driven optimization tasks. And that is something important for us, so that like when a problem occurs in field in a production compiler, we would know like, I mean, what is that needs to be fixed, right? So to cut a long story short, I mean, there's like plenty of challenges, but there's also, I mean, it implies that like there's plenty of like room for newer research in this space, right? I mean, just to point out, like, I mean, if you think about it, one of the things that popularized machine learning or deep learning in general programming community was this Netflix competition, right? I mean, recommending movies, right? Now when you think about it, we have come to a point we are able to offer a competition on using machine learning in compiler. For instance, Chris and his fellow members are offering compiler optimization competition for face ordering in the MLR machine learning for architecture and systems workshop. And you should actually check that out, because it's a way to think through, like, I mean, what are the challenges in bringing ML into compilers? How do environments like compiler gym can help us, and what extra that needs to be done to make this feasible and make it easily deployable in production compilers? So I mean, I would stop here, like, I mean, and open the floor for questions.
Thanks, Sandhya, for the excellent talk. If anyone has any questions, just unmute themselves and fire away. Okay, no one? Okay, Sandhya, you explained it so well that you have answered everyone's questions preemptively.
Thank you. So, I mean, if you have questions, like, I mean, please feel free to reach out to us. Like, I mean, we would be sharing the tutorial slides and the recording soon. I mean, basically, like, I mean, I just wanted to say that, like, I mean, this is a very interesting area, as you guys all know. And the main thing is that, like, I mean, there's plenty of challenges in taking these optimization to production compilers, and it would be great to hear your thoughts on, like, I mean, what challenges, like, I mean, you have run into, and where do you see, like, I mean, some of the solutions emerging. So do feel free to connect to us. Thank you.
Okay, so I guess, so we'll take a 10-minute break then, and then should we pick up on the hour for Dibyendu's talk? Does that sound good?
Hey, Chris, can you just stay on a minute just to check certain thing? I'll just play parts of my video so that I'll just intermix the two, just see whether it is coming up and you can see and hear.
Okay.
Yeah. So Chris is the.
So I can see the video, but I can't hear the audio.
Okay, you can't hear the audio, right? Just hold on. Let me unshare it.
Okay.
Yeah, just hold on. Yeah, let me share screen share. And there is share sound. Okay. Talking about applications of deep learning to compilers.
Okay,
Now
I can see and hear that now.
you would have heard cool. Both yeah. Chris and Sandhya.
Okay, great. So excellent. So should we give it 10 minutes to everyone?
Yeah, sure. I'll be back. So what I'll do is I'll play it intermittently and I'll be there to take questions and if there are certain things. Yeah. Okay. Okay. Thank you. I'll just wait out. Yeah.
Okay, I'm going to put up the placeholder slide. Okay, so I'll see you everyone in 10 minutes for Dibyendu's talk. All righty. To begin with, do you want to introduce yourself or introduce your recording? Just explain that this is a pre-record.
Okay, can you hear me, Chris?
I can hear you.
Okay. Thank you. So my name is Dibyendu Das, and I work with Intel in one of the projects involving deep learning accelerators. And today, as part of this tutorial, I'll be talking about some of the applications of deep learning to mainly compiler optimizations. You would have heard both Chris and Sandhya talk about interesting areas where some of these are becoming more and more relevant, some of the challenges and research directions, and now we'll delve into some of these in more detail for the next 50 minutes or so. So the way it will work is parts of it are pre-recorded, so I'll be starting to play that, but if you have a question, please stop me and I'll take the question. Maybe at certain junctures, I'll just stop the video and give you an opportunity to ask questions. So let's start. We will have roughly, I think, 45 to 50 minutes. Hi, good morning, good afternoon, good evening, wherever you are. My name is Dibyendu Das, and today, as part of this tutorial workshop, I'll be talking about applications of deep learning to compilers. Till this point of time, you would have heard both Chris and Sandhya introduce you the problem, looking at various aspects of it, the issues with data collection, research direction, etc. And at this point of time, I'll be taking you through a few compiler optimizations which have been designed of late, which applies deep learning, and we'll see what are the things that are being applied as of today. So as you can well understand that writing compiler optimizations is a hard problem, as many of you may already be aware. And the software stack is also becoming increasingly complex. So as you try to optimize more and more complex stacks, you may need to resort to more complex optimizations which need to scale to many, many functions or modules or files and things like that. And this increasing challenge coming from the software angle makes the job harder for the compiler writers. And as you can well expect, that correctness and performance of applications depend a lot on the compilers, and as a result of which the compilers need to be extremely careful as to what they implement. So for this particular talk, we need to see where we can target ML and DL techniques, which can ease and improve the compiler optimizations and help the compiler writer achieve a higher degree of precision and ease of use and scalability that will allow the optimization to be created or applied much faster, but in a correct manner compared to what we were doing till now. So if you look at the general compiler optimizations, usually they are modeled with two phases, an analysis phase and a transformation phase. And in the analysis phase, you are basically looking into correctness, you are looking into the cost benefit, you are looking into feasibility and things like that, mostly driven by heuristics. And at this point of time, there usually is no code change involved, because you are just applying the analysis to see whether it can be done, not done, if it can be done, how best it can be done. And then comes the actual transformation phase, where we implement a decision, and here the decision should be implemented such that the transformed code is correct. So you know about various complex optimizations like inlining, scheduling, register allocation. These are all, mostly in the realm of NP hard problems or NP complete problems and things like that. And decision making is approximated by, really, really complex heuristics, which are created and maintained over many, many man years. All right. So the first question is, what really do we want to target in terms of compiler optimizations? And we know that these problems are hard to solve, but at the same time, we also know that we need to, we are in the process of applying ML and DL techniques, which are by nature probabilistic in most of the cases. So if we are trying to apply a probabilistic model or algorithm or a similar solution to something where we want, in a way, deterministic answers and answers which are correct, then we have to be extremely careful. Also, we prefer cases where there's a large search space and it is difficult to carry out your heuristics or solutions in not an easy manner. And also approximate solutions can be preferred, and also you have available a large code or base or a sample which can be mined, from which we can do usually some form of supervised learning. Now, it's not always necessary that we need to do supervised learning, but in general, for many of the optimization that we'll see, people have started with supervised learning in a way. So there are three areas that we are going to, look at in terms of our optimizations and the ML and DL techniques we applied. These are like the optimization heuristics or phase ordering or some kind of a cost modeling. So going forward for the next half an hour or so, we'll be talking about several DL-based compiler optimizations. As I told you earlier, especially 5 of them. These are like taken from various parts of compilers. And the ones we're talking about are ETHMAL, which is a basic block throughput estimation, and is mainly a kind of a backend pass. Register allocation, also a backend pass. Auto vectorization using imitation learning, a kind of a middle end pass. Learned performance model for TPUs is a kind of a generic, if you want to say it. And then phase ordering via deep reinforcement learning, which is, again, a middle pass. The first one, let's go there. It's called ETHMAL, and it's basically trying to predict throughputs of basic blocks. So let's see what the problem we are talking about. In this problem, we are given a basic block of x86 instructions, just a basic block, not the entire your function with your control and data flow, but there's a basic block structure with x86 instructions, and you are trying to estimate the throughput in terms of clock cycles. Now, people who have tried to solve this problem would know that this is a hard problem, and usually people use some kind of analytical models. If you know about LLVM's MCA, which is the machine code analyzer, and Intel's ACA, which is the analytical model for the Intel processors. These are usually used in such scenarios, and we'll see later that the correctness of these analytical models may not be very high. I mean, we are still talking about maybe about, let's say, 15–20% diff from the actual cycles when they are run.
So why is such modeling hard? Because as all of you may know, that the modeling of a processor, or especially a modern processor core, is extremely complex, right? And this shows the core block diagram of one of the latest Intel processors called Cascade Lake. And you will see that there are many blocks that constitute this complex piece of hardware. And you have to model all of them. You have to model the front end of the hardware. You have to model its various buffers. You have to model its rename retire units, its schedulers, the ALUs, the ports. It's extremely complex. Not only that, for the person or the group of people trying to do this modeling, the specs are not always accurate. It may be accurate to a decent degree, but may have some details which are missing, some details which are proprietary. And, for a third party or people who are outside that particular company building the hardware, we may not get all the inputs required to do a very high fidelity prediction for the throughput of these instructions. So here, what Ithamal proposed was a data-driven approach using a neural net. And the way they tried to do that was they ran or trained a DL model using many samples of x86 basic blocks, and then measuring the actual corresponding cycle count on real hardware. And then they applied it for the inference scenarios. If you had a new hardware in the future, it's very likely you can apply some amount of transfer learning and retraining. Maybe need to modify the model a bit, but may not be by a high amount. So if you look at the high-level overview of Ithamal, you can see that there is, just hold on, let me get me a pointer. So you can see that here is your data set consisting of 1.4 million basic blocks from various benchmarks like SPEC and NAS. And then you feed it through your neural net, which I'll describe in a minute. And then you also run these through the actual cores to get the real throughputs, which is the ground truth, and you do a comparison and you do a back propagation through your neural net till it kind of stabilizes. Now, the kind of model that Ithamal used was a 2-layer LSTM, and I'll go through the details of what the 2-layer LSTM really means. So if you look at the basic block of x86 instructions, each instruction is consisting of a certain number of operands, and you'll have the registers and other kinds of things, but it's a kind of first level, if you can think of a first level instruction. And then the set of instructions of the basic block constitutes the next level of instructions, which finally encapsulates the total knowledge that is embedded inside a basic block to predict the final throughput number. So if you look at it, the way the solution moves is to first take each instruction. For example, you have a move ECX with a 0x02. So, in general, the constants are hard to encode. So here we'll be just encoding any constant with a special token called the const. So firstly, you will canonicalize into some kinds of tokens for each of these x86 instructions. And then these canonicalized tokens are now looked up through a token embedding table to give your initial vector embeddings for the first level of tokens of each x86 instruction. Okay. Now, once that happens, that goes to the first layer of LSTM. And in this layer, what you have is the maximum size of that LSTM is the maximum number of tokens that can be held in each access instruction, which is not a very big number, let's say in the low tens, right? And so once it goes to the LSTM, as you can see, you have a move instruction, you have an add instruction, and each one of them is going through its own LSTM. And the final vector embedding of the last LSTM cell is now fed to the second layer. So in a way, you can see that HMove is a vector embedding for the entire move instruction, x86 move instruction, and HAD is the vector embedding for the entire x86 add instruction and the specific tokens that were used for that in this particular case. And then this move and this adds are fed to a second layer of LSTM. And you can see that this is for each instruction in total, and then you will have the total number of instructions being fed to the next layer. Now, since in general there is no restriction on the number of instructions that you can have in a basic block, but if you look at realistic basic blocks, you may have only, maybe tens to a few hundreds. Usually it's not into thousands unless it's a heavily unrolled piece of code. So let's say if we restrict it to even something like 500 instructions or 1000 instructions, this is like, 1000 cell LSTM in a way, or 500 cell LSTM in a way. And then once you pass through this layer, you get the final encoding for the entire basic block, and you maybe pass it through some dense layers to finally get your prediction. So this is basically a regression problem, and you get the actual value of the predicted output or the predicted throughput for your basic block. And the results showed that Ethamol delivers much better throughput accuracy compared to the analytical models. And if you see that compared to LLVM-MCA and even ISCA, which is Intel's own architectural model, Ethamol does anything between close to 15% or 10% better than these analytical models. And this is for a whole range of hardware from Ivy Bridge to Haswell to Skylake. And if you probably redo those experiments with some amount of transfer learning and retraining for the next gens like Cascade Lake and Ice Lake, probably or most likely you are going to get a similar trend of results. So as you can see, this first problem or the solution we introduced called Ethamol is a very portable and robust approach. We really don't need to create analytical models again and again for new gen of hardware, unless and until that new gen hardware is I'll say, as a total or a major re-architecting of the microarchitecture or a major deviation from the earlier gens, in which case you probably need to redo your model in a bigger way. But still you can use this two-layer LSTM concept and maybe, play around with your hyperparameters and other things as such. So the code is in the following GitHub directory, and you are welcome to, have a look and even, try out a model like this for some of your initial cost model prediction. Now, people may ask, like you are talking about a basic block, what about the entire function or a program, and how do you handle control flow and data flow? So we'll go into a bit of that, may not be exactly the same problem, but a bit of that when I talk later about how you do a performance prediction for something like a data flow graph on a GPU. So with that, the first DL-based kind of a backend solution, has been told to you, and we'll go to the next one. The next one is a deep learning based graph coloring register allocation, and here we'll see how people have tried to use graph coloring for the register allocation problem. Now, most of you are with a background in compilers and you are already familiar with the register allocation as a graph coloring problem, but I'll still introduce it at a very high level. So as you know that it's an important problem in code generation, and since the number of registers available in most of the machines is lesser than the number of variables used or utilized in a function, we may not be able to keep all the variables in the registers and not do spill to memory and back. But for that, one of the earlier solutions proposed was to create something called the interference graph, and which models the registers which need to be live at the same time. And for folks who are familiar with interference graphs, you would know that it is nothing else but looking into some form of the backend IR representation. Let's say for LLVM, it maybe it's backend LLVM IR representation or the machine IR representation. For others, it may still be at their own IR level representation. So let's say we have something like what we are seeing here as your intermediate representation, and let's say you take the variable g, which is defined here, and you can see the last use is at this point and there are no uses of g after that. Then the liveness of g extends from this part to this part. Similarly for h and j, so j is considered live in, so there's no direct assignment to j here, but it's considered to be live coming into this particular piece of code, and this is the last use of j, after which we can say that the liveness of j ends. So the idea is if variables are live at the same time, they cannot be allotted the same register, because then there's a clash and you will get a correctness problem. So you create what is known as the interference graph based on the fact that if variables are live at the same time, then you're going to add an edge to it. Like for example, between j and h and g and k, we are going to add edges because they're all live at the same time. So if you complete the interference graph for this entire piece of code, you get something like this on the right hand side, right? And then the problem is modeled as a graph coloring problem, where we try to see, given the number of colors, which is the number of registers, how well we can color the graph. And then if we cannot color the graph, then we have to use some form of spelling. Now in this particular problem, we are not going to talk about the spelling issue. There are some other work that is happening today, I think most likely from the Google guys, who are trying to model the spelling problem using some form of reinforcement learning, if I'm correct. But here we take a much simpler approach, and we are just trying to figure out, without looking at the restrictions in terms of the registers, as to what kind of coloring can be done. Okay, so let's look at what was done for this particular solution. Is the problem was looked as a sequence-to-sequence translation problem, and the input sequence was nothing else but the adjacency matrix of your interference graph. And then we have a 3-layer LSTM, and for this 3-layer LSTM, the input to each of these LSTM cells is nothing else but the adjacency vector of each of the rows. So if you see that there are n nodes, then we'll have n LSTMs here. And then it passes to 3 cells. We have a dense ReLU, and you get the color. Now, once again, this problem can be modeled or should be modeled probably as a classification problem in a way. But when the problem was initially proposed, it was looked as a kind of regression with the number of colors being predicted. But if you look at if you look at this particular model, you will see that there are these 3 layers, and the inputs are all adjacency vectors. And for the solution that the authors proposed, they kind of restricted the size of the graphs to around 100 at that point of time. Most likely because of 2 reasons. One is the supervised training part of this problem required trying to figure out how to do perfect graph coloring, and doing perfect graph coloring for large graphs is pretty time consuming. You can do it within a reasonable period of time for maybe about 200 nodes, 300 nodes. Anything beyond that will take a large period of time, though it's an offline process and you can probably still do it, but that's an issue. And what was also observed was that for about 90-95% cases of spec benchmarks, the functions had around 100 to less than 100 nodes. There are only about 5% cases where the number of nodes were more than 100. There are only a few cases where the number of nodes were of the order of 500, 600, 700. Okay, so for those kind of cases, maybe a future solution maybe is to partition the graph into smaller components, color them separately, and then combine the colors in some form. Okay, so for this solution, if you see the one part we talked about earlier is that correctness is a major issue for compiler optimizations, and here you are using an LSTM where no constraints were encoded, and it's because in LSTMs it's difficult to encode constraints. So you will also see that there are solutions to the graph coloring problem using reinforcement learning. But if you look at the solutions, not only are the solutions complex, but they really would take very, very powerful machines to even train them, and they probably also would be pretty time consuming in terms of inference. So that's a separate question we would probably just touch upon later. But since constraints cannot be encoded, there may be cases once you do the training that for inference, the model may actually predict colors such that you will have some form of inconsistency. That means you may have an edge where the same color is applied to the 2 nodes at the end of the edge. So what we observed was that maybe about 10, 15, 20% of the edges were getting colored using invalid colors. And so the solution that was proposed was not to add constraints or not to try to add constraints to LSTM in an indirect way, but to make the algorithm a hybrid kind of algorithm, that you have a model where you allow the model to be as correct as possible, but let's say it's incorrect 10% of the time, 15% of the time, 20% of the time. We apply a very, very fast color correction algorithm after the model runs. And this is a usual algorithm. There's nothing deep learned or machine learned about it. This is a normal algorithm that runs. So what happens is, let's say you have this famous graph called the forest fire graph, which has a chromatic number of 5. And when you color it through the LSTM-based model, we actually color it with 4 colors, which results in 2 invalid edges, where you see that this edge from 2 to 3 and edge from 1 to 5 are invalid because they have the same color. So in the first case, it is the color is C3, and the second case is C2. So what we do is, instead of trying to do something fancy, we apply a very fast color correction. So here, if you see for the edge C2, so from node 1 to node 5, you can see that since color 2 is used and there are other colors that are available, right? Because finally we have colored with 4 colors, we actually can break the tie or make the invalid edge valid edge by coloring, let's say, node 5 with color 3, right? So there, the invalidity is broken, and you have not increased the number of colors. But it's not always possible. For example, if you take the edge between node 2 and 3, they have the same color, but there's no way you can break the invalidity and still maintain the same number of colors. So you have to add an extra color. So you see, at the end of the day, it's all nice and good because you still get a chromatic number of 5 for our new hybrid coloring algorithm with model based plus local, what we call as local correction. Okay. So now comes the fact that how useful is it? I mean, though the authors did not do a real implementation of this in current compiler, but what happened was there was still an evaluation that was performed by looking at a comparison between this DL model and what happens with LLVM's GRA. So this is the path usually taken by LLVM's GRA, where you have the live interval analysis followed by a spill weight calculation, a priority queue construction, registration, assignment, eviction, split, and spill. And the LLVM's GRA doesn't really do the interference graph explicitly. So the live interval analysis was tracked, and for the LSTM model specifically, the interference graph was created. And for Spec 2017 benchmarks, what was done was once the interference graph was collected, the LSTM-based model was applied to do inference and figure out how many registers were predicted by this model to be required for the coloring of those interference graphs. And then it was compared with the actual number of registers that LLVM used during its code generation, right? Now, this may be a bit of an apples and oranges because there are other restrictions in terms of register classes and things like that. But even if you take it with a bit of salt, the comparison is fair in a way. And then if you look at the numbers that were shown in the paper, you'd see that in several benchmarks, the DL model was at par or doing better than LLVM's GRA in terms of how many registers it could have used to actually color this interference graphs from the real functions that were taken from Spec 2017 benchmarks. So the code for this is available once again on GitHub, and you are welcome to look at it. Now, two of these are over, and we go to the third one called the compiler auto vectorization using imitation learning. We saw the first two as some kind of an LSTM-based setup, and this is the first one we'll see, which is based on reinforcement learning. Now, in this particular piece of work, the authors try to solve the SLP or the superword level parallelism problem using machine learning. And as you may know, SLP problem tries to figure out what you can vectorize in a straight line code or in a basic block rather than in a loop. So if you look at the SLP problem through the lens of ML and RL, what you are trying to do is, let's say you have a starting sequence of code like this shown here, and you mainly would like to use some kind of neural network strategy to get to a point where you can do the maximum amount of vectorization. But you have to be careful because, once again, correctness is a major problem in vectorization other than performance. And then naive ML strategies may lead to correctness issues, because if you see on the left-hand side, the first four statements are isomorphic, but not the last one, right? So if you vectorize right by the way it is shown on the right-hand side by combining statements 4 and 5, it will be wrong, because for one case you have a plus operator, in the other case you have a star, which is a non-isomorphic operation. Though, by the way, let me state that in some hardware like x86, actually there are instructions where you can apply plus and star together, kind of in an isomorphic manner, but let's keep that aside. But in general, you have to be careful to make sure that if you are applying a neural net based model to do your vectorization, you have to make sure that you maintain your correctness. So as you know that in the RL formulation, you need to have your Markov processes, and you need to have your nodes, the Markov states, and the edges or the transition between these Markovian states. So let's say you start with what is shown on the left-hand side as your first state, and you try to go, as I told you earlier, to the state of maximal vectorization. And from each state to the other, you have a set of valid actions. For example, from the left-hand side, as told earlier, you can probably pack A1, A2, or A2, A3, or A3, A4, considering the fact that, you can pack a max of 2. If it was 4 or something, actually you could have packed 1, 2, 3, and 4 together. But let's assume for this case, you are able to do only a pair packing problem. So if you do a pair packing and you have to choose a valid action, and you choose, let's say, A1 and A2, you have to go to a new state. And why do you choose A1 instead of A2, A3, or A3, A4 will be based on something called your reward function, right? So based on that reward, you will probably go to this new state, and then from that new state, you once again choose another valid action to go to your next new state, and so on till you reach your state of maximal vectorization. Okay, so there are some details in terms of the MDP formulation state. Right now, it may not be very important, but I'll go through very quickly. The state actually consists of various kinds of nodes, right? You have the regular instruction node. You may have what is called the packing node, represented as P here in this diagram. You can have an unpack node, which is represented by UP in the diagram. You may have a constant or a focus node, depending on which pair of instructions you are trying to vectorize next. And similarly for edges, you may have different kinds of edges, whether it's a dependency or a package or a possible package or a focus edge and things like that. So now let's get to imitation learning. So what do you do? So you have to find your policy network once you have your MDP states. And what the policy network tries to do in this particular case is try to use imitation learning. And the authors of this work actually had solved a similar problem earlier of SLP using ILP solvers. And so what it does during the course of imitation learning is they try to build a graded graph neural net for the policy network, and then this graded graph neural net tries to imitate the steps of the ILP solver given the initial state to actually predict which action to take among a set of valid actions depending on certain runtime estimates and cost and reward function. So mainly, if you see, the GGNN is actually working as a kind of surrogate or substitute for your ILP solver, right? And it is actually not trying to really solve it using any kind of ILP formulation or something like that, but just kind of as a surrogate mechanism to get to your best policy. So that's all I'm going to.
So I'll stop for a brief while and take maybe a couple of questions if there are any, and go to the last two.
Just a brief question, Debyendu. What is MDP?
MDP is the Markov decision process.
Okay.
Yeah. Any other question? Okay. We'll go to the last two, and we can take any further question at the end.
Talk about for the auto vectorization part of the story. So here you can see that an SLP vectorization problem can be formulated with the correctness as well as performance based on the rewards using a reinforcement learning model with the MDP states and a policy network based on graph neural net which tries to imitate some kind of ISP solvers. The next part, I'll be talking about learning a performance model for TPUs. As I told you earlier, that in Ethamal, we look just at the performance for a basic block of x86 instructions, but taking this one step next, if you are interested in finding the performance of a program on the underlying hardware, you may need to do something that is more than a two-layer LSTM-based model that was done for Ethamal. So in this particular problem, the authors tried to learn a performance model for XLA graphs. For folks who are not familiar with XLA graphs, there's nothing else but the data flow graphs that are produced out of a TensorFlow program, right? So you will have, if you're familiar with TensorFlow programs, you'll have your high level computational operators, and then you'll have some kind of a dependency, which are nothing else but how the tensors pass between these operators. So just think of it as some kind of a data flow graph where their nodes are really operators operating on your tensors. And then the idea is to take this data flow graph and then predict how much performance will come out of it if you run them on a modern hardware AI accelerator like a TPU, which consists of some amount of matrix multiply engines and then some amount of vector processing surrounding it. So, if you look at the data flow graph, it looks like this. You will have these nodes, which are nothing else but the deep learning operators, right? Let's say your softmaxes, your norms, and things like that. And your normal maybe adds and casts and GALUs and ReLUs and LUs. And you need to figure out the performance of it. And so if you look at how a kernel is defined, a kernel is nothing else but a combination of these DL operators. And so there may be some other program which takes this DL operator and then figures out that I want to have this bunch of operators as one single kernel due to various reasons, and this bunch as another single kernel consisting of these other operators. And then for each of this kernel, I want to predict what is the amount of time taken to run this kernel on a TPU. And in this particular problem, the authors are going to train a deep neural net to map these kernels to the runtime estimates using so this is very briefly the model architecture. Will not go into all the details, but if you see the main characteristics of this is the DL operator will have some amount of DL op embeddings. They may be learned embeddings, they may be table driven, but these are like basically you can consider them as features of this operator. Like if it's a softmax, if it is a reduction, if it is element wise, there are certain characteristics of this DL operator which will be embedded. And then you may also have other node or operator features that that you can extract. In addition, you will have this full data flow graph, which is also represented using an adjacency matrix. We used a similar technique. We saw that similar technique was used for the register allocation problem also. Now, this adjacency matrix, along with this DL op embeddings and the node op features, are concatenated and passed through a graph neural net. Now, for people who are familiar with graph neural nets, you may know that what the graph neural net try to do is, kind of propagate the feature set of each of these nodes along the edges and then try to get better embeddings for your nodes. So actually, we could have dropped this particular graph neural net and even then gone through an LSTM, which would have been very similar to what the Ethermal solution would have been. But since we have a data flow graph consisting of these operators, if you use a graph neural net, the expectation is that the embedding or the vector representation of these nodes would be much better or more precise if it flows through a graph neural net. So once it flows through a graph neural net, you have the final embeddings of all your nodes. You can actually then do a topological sort on your data flow graph. And then once you topologically sort the data flow graph, you take each one of these nodes and feed it to the LSTM. Once again, let's say data flow graph consists of 200 up to 200 nodes. So you'll have up to 200 LSTM cells, and you pass through some linear layers and then finally predict your runtime. So the application of this kind of a learned model in this particular work by the team at Google was mainly to figure out the best tile selection, which is some kind of how do you chop your memory to have better performance, as well as something called operator fusion, where you try to combine multiple DL operators to a single DL operator so that you have less traffic to memory and you reduce your memory bandwidth requirements. So in the first one, there may be various valid tile sizes, and this particular learned model is used to obtain the relative performance rather than an absolute performance between these tile sizes. So a kernel, it seems, can have up to maximum of 500K tile sizes, and then for training, they had 25 million samples and kind of did a supervised learning model for this. Similarly, for operator fusion, they had about 200 million samples with about 50K fusion configurations. And once again, the learning was based on this kind of data. So now going into the final DL-based technique, we saw first two techniques based on LSTM. We saw the third technique based on RL. We saw the fourth technique based on a combination of graph neural net and LSTM. And there's a fifth technique which talks about basically the phase ordering problem, which is one of the most important problems in compiler optimizations using deep reinforcement. So as you know, the phase ordering problem is a very important problem in compiler optimization because we have a large number of passes in any modern compiler. LLVM pass infrastructure can have anything between, usually 50 to 100 passes at the higher optimization levels. And each pass may have several tunable parameters, making the problem extremely hard to solve. And if you want to enumerate all possibilities, it creates a huge search space, and it's really, really complex. So how do you pose the problem as an RL problem? Is the IR can be a kind of a state. We'll see that it has to be embellished with something more to make it a kind of an MDB problem. But let's say the IR resembles a state, and then the passes can resemble actions. And then with one particular pass, you can transform this IR to another IR, and it can probably give you better performance. With another pass, you transform it to another IR, and it may probably give you worse performance. So your optimizer is the environment, your passes are your actions, and then the rewards are, let's say, either actual runtimes or approximations of your runtimes, whichever works for you. So in this particular RL approach, you are trying to learn once again, the value function, which is based on your state and actions, and has the reward as well as your discount factor. Okay, and for the reward for this particular problem, the authors used the log of the runtime for the current state divided by the runtime for the next state, so that you get kind of log value of your speed up. So if you look at this particular figure, this gets a very high level view of how it will work. You have your input, which let's say is your IR, which is a .ll file from LLVM. And you have an agent history. Initially, the action history is like empty. And the agent will now try to choose the actions among several few based on the reward it gets. And let's say it picks up the max among all the rewards and takes a particular action and records it and also applies the particular transformation associated with that action, gets a new LLVM optimized IR, and again feeds it back to this cycle till you finally converge, or you get a reward which is not positive anymore. So this can still be a big search space and time consuming problem because of the hundreds or maybe several tens of passes that we have. So what the authors decided that you can actually divide up your actions into several levels of abstraction, okay, which I'll go through later. So if you look at the IR is encoded using the neural code comprehension vector embedding work done by Ben Noon and others. And the action history is one hot encoded. So state is the agglomeration of the action history and the IR, which makes it a Markovian decision problem. And once that state vector embedding is done, the actions are actually divided into three levels of abstraction. As I said, you consider H, M, and L. In H, it actually is a group of passes. For example, let's say you have 100 actions, you can group it up, first 10 into one, the second 10 into other. For this particular work, authors have actually done a more logical grouping rather than a blind grouping of the actions. And then in M and L, you may really have the real passes being given as actions at the lowest level rather than grouping them up. If you use H, as you can see, the search space become much smaller because the number of actions you can take is actually reducing. For example, instead of 100 possible actions at each state, in terms of your optimization, you're probably applying only 10 or 5 or even lesser than that if you want it. And then you pass it through the general alert framework, and you finally get your result that given an input program, I want to apply my 50 passes in this particular order to get the best output out of this. So if you look at it, the phase ordering problem has been static all through, based on compiler engineers' knowledge, based on the benchmarks and things like that. But with this kind of an RL formulation, it becomes dynamic, that for each program at hand, you may apply a different kind of sequence of optimizations to get the performance as best as possible for the input sequence. Okay, so I'm almost like at the end of my talk, and as you can see that I have presented to you 5 deep learning based compiler optimization techniques from various phases of the compiler, starting from the back end, the middle end, and even something which is generic, which may encompass all the phases. So in conclusion, you are at the cusp of utilizing DL techniques for compiler passes, and it's a big challenge to ensure correctness because, as you may know, unless you're correct, even if you provide performance, it doesn't work for compilers. In the proposed work, we have seen NLP-like techniques, we have seen reinforcement learning, we have seen graph neural nets. These are all becoming very popular in terms of usage for compiler optimizations, though there is no consensus yet on standardized program representations and how to represent control flow and data flow, whether it's graph neural net, whether it is something else. So the open questions at this point of time are, how can we generate semantically correct transform model using deep learning? And would the optimization of the future be a mix of deep learning and fast correction algorithms that we showed you for graph register allocation? So which means that you get most of it right by applying the DL model and then apply a quick correction pass instead of trying to get everything right through the DL model. And the other part is, can these models be really portable, right? So once you build it for one compiler, can you take it to another compiler? Can you take it to another hardware? And how much of transfer learning can you really do for some of these problems? So, you know, this is what I had to tell you for this particular workshop of lecture. Hope you enjoyed it, and maybe we, follow up on some of these work and papers and techniques, and maybe you can start applying some of these in your own work. And hope to hear from you soon from the reports of those work and how you fare. So thank you very much, and thank you all for giving Chris, Sandhya, and myself this opportunity to present at this particular workshop and tutorial, and maybe we can take some questions now. Thank you very much.
Yeah, we can take some questions maybe together for all the parts, if there's still something pending, or maybe a few for my set of slides, whichever works.
Hi, Debiadu, a quick question, if I can.
Yeah, sure, go ahead.
So, so you talked about learning the performance model of assembly instructions, but compilers use cost models of IR operations to guide their heuristics. Is there an attempt to learn a good cost model for IR operations? Because the reward is usually not assigned to a given transformation along the many passes, right? It's, you need to get down to the assembly so that you can really get an actual reward back, right? But we want to, if possible, to get a cost model for IR operations in midstream.
Okay, so are you talking about something like I'll not say replacement, but something equivalent to a TTI in LLVM?
Yes.
Okay. Yeah, I mean, I have some thoughts about that, but I don't know. Maybe I'm unaware, but maybe there's some effort happening on an equivalent part. You raise a very good question, because today, let's say in vectorization or many other optimizations that we do, we actually look at the TTI to get the cost of a single instruction in a way, and then let's say get the vectorization cost of it, and then compare with the scalar, et cetera, et cetera. And we have personally faced these problems working as part of our Intel DL stack, that even for certain cases that was not enough, because many of our instructions down below are, let's say, VLIW, and they have other complex characteristics, and just looking at the TTI cost of a single instruction probably is not good enough. So I think there are already some efforts, and something will happen, I'm sure, in the future to look at, let's say, a bunch of IR and it's nothing else but raising the, I'll say the input from your x86 to the IR, even let's say LLVM, not just LLVM IR, maybe even MLIR. But there are some questions, I think Sandhya and I were discussing it some time back among ourselves, that there's a question that arises that with x86, it's easy because you are getting the code really at the end of all your transformations in a way, and there is nothing else that you're going to do. But with the IR, that is not the case. IR is going to get transformed over many, many passes. And if you, let's say you are doing training, you need to make sure which pass you are taking your training inputs from. Let's say if you're taking training inputs from very early in your IR set, that may not look very similar to what your IR will look like very at the end of your, let's say your O3 passes, or in the middle or somewhere else. So that still, I think, will be a major challenge for the IR part of the story, that which part of the LLVM are you going to track for your training sets and things like that. if it's just a single pass, maybe it's okay. Let's say you are just doing vectorization, maybe pre and post is probably good enough. But if you're going to do a general IR modeling, that still probably remains a bit open. Maybe you can still take a mix of passes, but may not still be good enough. But that's a good question, Eyal, right? So, but I think, yeah, so somewhere down the line, I think people will start thinking about replacing TTI with IR-based model or MLR-based model or things like that. And this question need to be answered there. But I don't know it has been solved. Maybe someone's still working on it, but yeah, good.
Sure, thanks.
Yeah, thanks, yeah. Chris, any other question from the audience?
I don't see anything in the chat.
Okay. So maybe I'll hand over to you.
Sure. So yeah, well, thank you, Dibyendo, for the talk. So let's just leave it open for one more minute in case anyone has a last question for either Dibyendo or Sandhya or myself. And then after that, we'll wrap up. Okay, I guess everyone's ready for lunch. So in that case, yeah, thank you, Sandhya and Dibyendo, for the talks. And most importantly, thank you everyone who joined our tutorial. This was a lot of fun. Hopefully you all learned something. I think our contact details are available somewhere if you would like to follow up offline. If not, I'm sure we'll find a way through Hoover that you can reach out to us. So in 30 minutes in this room will be the next tutorial, which will be all about CompilerGem and a bit of hands-on hacking. Until then, we'll be on break. I think I will kick everyone out of this call because I need to do that in order to end the recording. But you can rejoin the same link, I think, in 30 minutes, and I hope to see you all there. So thank you very much.
Thank you, Chris.
Hey,
Bye, everyone.
Yeah, thanks to the organizers. Yeah, bye.